it is an honor to be invited to this Digital Futures seminar series and to present our recent research on integrated sensing and communications. Okay, so here is a brief introduction of myself, and I guess you have all learned this from Deyu's introduction, so I will not spend time on this. And today, I'm going to introduce, I'm going to overview the theoretical framework of integrated sensing and communication technology. And my talk will be composed by 7 parts. First, background and applications, and then ISAC performance trade-off, ISAC Waveform Design, ISAC Receiver Design, communication-assisted sensing, and sensing-assisted communications. And finally, a summary. So let's first look at the background of this technology. So the background of integrated sensing and communications are twofold. So first of all, there are technical forces. So we can see that after all these years development, radar and communications are now going to higher bands, larger antenna arrays, and miniaturization. And the radar and communication become similar, more and more similar in hardware architecture, channel characteristics, as well as in signal processing, especially at a high frequency band like millimeter wave and a terahertz band. And of course, many emerging beyond 5G and 6G and IoT applications require integrated sensing and communication designs. And there are also commercial forces in this aspect. So sensing is well recognized by the communication industry as a basic service and even a native capability for the next generation wireless networks, such as Wi-Fi 7 and B5G and 6G. So I will detail on this later on. And there are some novel civilian radio sensors like the SOLI sensors developed by Google. So they are facing challenges from spectrum regulators worldwide. So as far as we know, SOLI is now still restricted to be used in many countries due to the spectrum regulations. And of course, there are spectrum congestion problems, as we are now demanding more and more spectrums for the wireless communications. So on the basis of these two aspects, the technical forces and commercial forces, there's a need to integrate sensing and communication functionalities. And then this motivates the research on so-called ISAC, so integrated sensing and communications. And we give the definition of ISAC as a design paradigm and corresponding enabling technologies, while sensing and communication systems are integrated to efficiently utilize congested resources and even to pursue mutual benefits. So there are 2 aspects in ISAC. Okay. So we can see that there are actually 2 gains in ISAC technology. One is a so-called integration gain. That is to see in the previous systems that sensing and communication are individual systems. And now we have these integrated systems that can perform both functionalities. Like in this figure, we have a dual functional radar communication access point that can perform multi-user communication and can detect, for example, incident detection, and to monitor UAVs, and to cover this high-speed vehicular channels. Okay, so by this integration, we can have the improvement in the efficiency. So this includes spectral efficiency, energy efficiency, and hardware efficiency, because now you can have a single device, a single spectrum, and a common signal to do both communication and sensing. Okay, so we have an efficiency improvement, and accordingly, we will have cost reduction we have hardware cost reduction and signaling cost reduction. And there are some fundamental theory here, like the information theory and signal processing, to reveal the fundamental trade-off in this scenario, okay? And of course, there are a second gain we call coordination gain, while communication and sensing can assist each other. So there is communication assisted sensing or sensing assisted communication. So in this scenario, we call it a sensing as a service. And this is a vision actually for the B5G or 6G networks, which we call perceptive cellular network, while the whole wireless network will become a large sensor network. So this will lead to the perceptive cellular network. And this cellular network can do many things like channel knowledge map construction, mobile crowd sensing, localization, tracking, drone monitoring, and cooperative localization, imaging, human counting, and so on. So there are some key techniques here like cooperative sensing, beyond line of sight sensing, network sensing, and performance analysis. And with this perceptive cellular network, we can also have sensing assisted communication. So we can use active sensing instead of in the previous designs, we have device-based sensing. And we can use this device-free sensing to do sensing assisted communication to assist many high mobility communication scenarios like in V2X, like in UAV network and high-speed railway network. And we can monitor the movement and the variation of the vehicles or the channel by using active sensing in real time. And in that sense, we can assist the communication. So there might be some key techniques here like sensing assisted wireless resource management. And here, if we have a vehicular network, we have sensing assisted platooning and extended sensor and SLAM, of course. Okay, so this is the second again, the coordination gain, which is upgraded level of the integration gain, actually. So let's then look at the historical development of this technology. So actually, the first ISAC signaling scheme was proposed very early, so can be traced to 1963. So this is a very old paper on carrying communication bits using the radar pulse interval modulation. And as you can see, in the 1994, there's the first patent on MIMO communication system is granted in the USA. And in 1996, there's a so-called project initiated by the Office of Naval Research of the US. So this is called Advanced Multifunction RF Concept, which aims at to integrate the communication and the radar functionality by using a single RF front end. So this is called Advanced Multifunction RF Concept. And so then because of this project, so motivated by this project, there are lots of ISAC research going on during the first decade of, last decade actually. So you can see in 2003, the first ISAC scheme that exploits chirp signals. So chirp signals is a very well exploited signal in the radar signal processing. And in 2004, the concept of collocated memory radar is proposed by the MIT Lincoln Laboratory. So this is actually motivated by the MIMO communication. And in 2005, the so-called hybrid and analog digital structure was introduced into MIMO communication. So this is actually earlier than what we know as the millimeter wave communication. And in 2010, so Mazeta's seminal work on massive MIMO communication was published. So this technology has become the core technology of our 5G wireless networks. And in the same year, the concept of phased MIMO radar was proposed. So the phased MIMO radar is actually a trade-off between the so-called phased array radar and the MIMO radar. And it is exactly the parallel of the hybrid beamforming structure in the communication as in the radar sense, okay? So it is actually a trade-off between phased radar and MIMO radar. So you can see that communication and radar are inspiring each other during these decades. And in 2011, this is a very important paper that which has exploited OFDM-based ISAC signaling. So using OFDM communication signal to do sensing. So this could be the very first work on this technique. And then in 2013, we know that NYU Wireless landmark paper on millimeter wave mobile communication is published. And in the same year, DARPA launches another project which has explicitly mentioned that we should have a shared spectrum access for radar and communication. So this is to release part of the radar spectrum for the use of commercial communication, so spectral coexistence. And after 1 year, we can see that the hybrid analog digital technique is applied to the millimeter wave MIMO communication system to reduce the number of RF channels, millimeter wave RF channels, to reduce the cost and energy consumption. Okay, so as you can see that, another highlight is that last year, there's a first theoretical analysis of the asymptotic performance of the massive MIMO radar. So you can see during this decades, radar and communication are always inspiring each other, okay? So the research on ISAC has also been tremendously accelerated over the recent years. As you can check on IEEE Explore that during this 40 years, 50 years, this is the first 100 IEEE papers on ISAC. And during this 4 years, the second 100 IEEE papers, and this 2 years, the third, and the 2019 up to now, the fourth 100, maybe more, okay? So the research on this topic has been tremendously accelerated. And these are some of the academic activities related to ISAC. So these are journal special issues on GSAC. This is organized by us. And the GSTSP, IET signal processing, GSAIN. So this is a Chinese journal on communication and information networks. And there are lots of conference activities going on. So on major communication conferences like ICC, WCNC, Globecom, and radar conferences, on signal processing conferences, SPOC, ICASP, and also there are even dedicated conferences like this two, actually International Symposium on Joint Communication and Sensing. So this might be the first dedicated conference on ISAC, or in their words, on GCNS, so Joint Communication and Sensing. Okay, so the scope of ISAC is actually very multidisciplinary. So as far as I can see, there are actually lots of IEEE societies involved in this in this topic, actually. So from the basic information theory to review the fundamental limits and trade-offs in ISAC. And of course, we have signal processing, which which are mainly my work on design dual functional waveforms and joint signal processing frameworks. And mobile computing to detect and recognize events and activities via commercial wireless devices. And aerospace and electronic systems, this is actually a dedicated society called IEEE AESS. So this is a society dedicated to radar systems and navigation systems to embed communication function into radar. And there's, of course, intelligent transportation systems or vehicular technologies to leverage ISAC in V2X and autonomous vehicles. So as we can see, there are at least 7 societies of IEEE involved in the research of the ISAC, and maybe more. For example, the Microwave Technology and Techniques Society, so MTTS, they are also considering to, for example, design a novel front end of integrated sensing and communication systems. Okay, this is the scope of ISAC. And here are some industrial efforts on this topic. So this is actually a bit of old news, which was happening last year, November. So Huawei identifies ISAC as one of the 3 major scenarios in their vision of beyond 5G or 5.5G. So in this year, they have explicitly proposed that ISAC can be one of the key techniques of their 6G vision, okay? So in Ericsson 6G white paper, they have mentioned sensing as an enabler for the cellular networks. And here in NTT Docomo 6G white paper, they have extreme massive connectivity and sensing. And in Nokia Bell Labs, they have proposed a unified millimeter wave indoor systems to combine communication and sensing. So these are some of the industrial efforts, and there are lots of other companies that concern about this technology. So this is another effort, which is perhaps the first international standard for sensing, which is actually AO 2.11 BF, so WLAN sensing. And the definition of WLAN sensing is to use the use of received WLAN signals to detect the features of an intended target in a given environment. And they have already defined a number of use cases and KPIs. Okay. So given the previous academic activities and industrial efforts, we feel that it is very necessary to establish a research group or research organization to integrate the ongoing and future planned ISAC related events. And so we have established this Integrated Sensing and Communication Emerging Technology Initiative, ISAC ETI. So in this ETI, we actively support and promote ISAC related academic and industrial activities, and by gathering together the relevant researchers from different communities, like I said, from the information theory, signal processing, mobile computing, radar systems, vehicular technology, and intelligent transportation systems. So this is a founding leadership team, and this is me and the academic chair, and this is Dr. Tony Xiaohan from Huawei, who is the industry chair. And this is a vice chair from the US, Athena Petropoulou, Professor Athena Petropoulou from the Rutgers University, and Professor Christos Massoros from UCL, Professor Jie Xu from Chinese University of Hong Kong, and Professor Tanner Lee from the Temporary University, and of course, 2 vice industry chairs from Huawei and Intel, and our secretary, Dr. Yuanhao Cui from BUPT. So this is a founding leadership team of the ISAC ETI. Okay, so the previous slides about the background and the motivation of the ISAC research and some of our efforts on integrating the academic and industrial activities. So from this slide, I will begin to introduce the theoretical foundations of ISAC. So this is actually based on our recent overview paper submitted to IEEE JSAC. So there are actually, so based on my understanding, the ISAC can, the theoretical foundation of ISAC can have these aspects. So we have performance trade-off So this will include basic information theoretical limits, trade-off in physical layer, trade-off in the channels, trade-off in cross-layer designs, and signal processing, which in which case we have waveform design, we have receive signal processing, and communication assisted sensing. So how to build a perceptive mobile network, how to use the current cellular network infrastructure to support the network sensing and the sensing assisted communication. Okay, so the first two aspects is about the integration gain. So remember the definition of integration gain, which is to improve the efficiency, and the last two parts is about the coordination gain, which is to have the mutual assistance between communication and sensing. Okay. So let's first look at some performance metrics of sensing and communication. So the sensing operations can be roughly split into these three categories. So detection, estimation, recognition. Detection is to make a binary or multiple decisions on the state of a sensed object. For example, is a target present or absent? Is this guy sleeping or not, standing or not? Okay, so this is a detection problem. And estimation is to extract useful parameters of the sensed object from noisy or interfered observations. So, for example, the localization, the coordinates of the target, the angle, the range, the velocity. Okay, so finally, the recognition operation is to know what the sensed object is. Okay, and there's of course another operation called imaging, but imaging can be actually decomposed as lots of basic detection and estimation operations. So these are some basic sensing operations. And from the communication perspective, we usually evaluate communication performance from two perspectives. One is the efficiency, another is robustness. So efficiency is to evaluate how much information is successfully communicated from the transmitter to the receiver, given limited available resources. So in the efficiency aspect, we can have spectral efficiency or energy efficiency as two typical metrics. And the robustness, which is to measure the ability of a communication system to reduce or even to correct the errors in the transmission in the presence of noise and interference. So for robustness, we have metrics like bit error rate, symbol error rate, and the frame error rate. And for sensing, for detection, we can have detection probability or false alarm probability as two typical metrics. And for estimation, we can have mean squared error for the estimate of given parameter, and we can have a parameter bound, which is the lower bound of all the unbiased estimators in estimation. So these are their definitions, and you can look into the details from this paper. Okay. Okay, so some basic problem in the theoretical foundation of ISAC is a so-called ISAC resource allocation, which is also the motivation to study the trade-off between sensing and communication functionalities. So from a naive perspective, a very straightforward perspective, that we can actually have orthogonal resource allocation on sensing and communication. So in this sense, we can have time division, spectrum division, or spatial division. So this means that we can have orthogonal resource allocation to at a time domain, spectral domain, or spatial domain for communication and sensing. So for example, here we have these two blocks as sensing signals and these two blocks as communication signals. And here we have these two frequency bands as communication and these two as sensing. And here we can use two spatial resources like antennas as sensing and another two as communication. And of course, we can have a unified resource allocation, which means that all the resources are reused between communication and sensing. So there's no orthogonal divisions between them. And in all these cases, actually, because the resources are limited, so when wireless resources are shared between communication and sensing functionalities, performance trade-off naturally arises due to their contradictory design objectives. So like I said in the previous slide, because we have different performance metrics for sensing and for communication. So when we design the ISAC systems, then there will be contradictory design objectives. And if we're going to share the wireless resources between them, there's an inherent performance trade-off between them. So then let's look at the details of the performance trade-off. So the first one, of course, is the so-called information theoretical limits. So from the fundamental theory. So actually, the information theoretical limits between sensing and communication is not a new story, because in this very classical paper published by Dongling Guo from the USA on HVA transactions on information theory, this is a paper published on 2006. So they propose a very elegant equation, which is known as IMMSE equation. So in the left-hand side, we have mutual information. So I, denoted as I. And in the right-hand side, we have IMMSE, which is the minimum mean squared error. So they are both functions of SNR, okay? And consider that you have an input and an output of the, you have a channel, you have an input, and you have an output, and you need to measure the mutual information between input and output, and you can also recover the input from the output. Then there's an MMSE here. So this equation elegantly connects the basic metrics on information theory and estimation theory. Okay, so you can see the derivative of mutual information is actually half of the minimum MSE. So they are both functions of SNR. So this is also this can be also verified by like we all know that Gaussian input will maximize the mutual information, but it also maximizes the MSE. So essentially, Gaussian inputs of a channel can be the favorable, most favorable for the information theory, but can be the least favorable from the estimation perspective. So this is a so-called IMMSE equation. And then there's another research on the so-called capacity distortion trade-off. So this is also a very old research, which was actually proposed on, let me see, maybe 2001. Okay, so this is actually a very classical paper by Thomas Carver's group. So Thomas Carver, maybe everyone knows his book on elements of information theory. So they have studied this problem called so capacity and state estimation for state-dependent channels. So what is a state-dependent channel? This means that the distribution of this channel is dependent on a state S. Okay, so we in this setup we have an encoder which wishes to transmit pure information, a message W, to the decoder. Okay, and by passing this channel, state-dependent channel, and in addition to this pure message, the encoder also wishes to transmit the state of the channel S to the decoder. So at the decoder, it wishes to recover the message W and estimate of the channel S. So we have a W hat and an S hat here. So this is, in fact, a joint problem of message decoding and state estimation. So there is a metric for pure message transmission, which is called the capacity. And there is another metric called the distortion. So the distortion is actually defined as this. So this ds as s hat and the true value of s, some distant metrics to measure the distortion function and their expectation. Okay, so this is, there's an inherent trade-off here where you have to decode a message and at the same time to estimate the state of the channel, okay? So there are inherent trade-off, which is called the capacity and distortion trade-off. But this is actually not exactly the radar system setting, because in the radar system, the transmitter or the encoder does not know the state of the channel. So that is, so this is actually a very different system setting, but it has a similar insight in the system, in ISAC system that we're studying. So I think in the last 2 years, there's lots of research been done by Professor Mary Kobayashi and Giuseppe Kerr from TU Berlin. So what they have done is to model the radar system as the radar channel as a feedback channel. So imagine that your radar system transmits a signal and hits a target, and this target will reflect an echo to the radar system, to the radar receiver. And this channel can be somehow modeled as a feedback or delayed feedback channel, okay? So which is like here, we have again a transmitter and wishes to transmit information to the receiver. And this is, again, a state-dependent channel, but with a delayed feedback, which means that when we transmit information, then this channel will output a Y to the receiver, and the feedback is state, a delayed state to the estimator, okay? So this is somehow mimics the radar operation of using the echo signals to detect the target. So by using this system setting, they have defined this capacity distortion trade-off or CD trade-off as actually an optimization problem to maximize the mutual information between X and Y and given the state S. And then subject to the distortion metric, the expectation of distortion between S and S hat should be less than some threshold. So this is the CD trade-off, and this is their results. And if you have a joint approach where you use a joint signal to do both, then you can have a trade-off curve like this. But if you use separation-based or orthogonal resource allocation, like I just introduced in the previous slides, then you will end up with this poor trade-off curve. Okay, so these are some information theoretical limits analysis on communication sensing. So we also observe some more trade-offs in the physical layer designs, while you will have a concrete performance metrics, concrete waveform designs, and you need to have to reveal the basic trade-off between the concrete performance metrics in addition to this information theoretical performance metrics. For example, you can have detection versus communication. And this is from another paper. This actually signal processing letters. They have proposed a passive radar and the communication joint system, while they have orthogonal signals, orthogonal resource allocation, one for radar and one for communication. So the power is split into the radar power and the communication signal power. And they wish to optimally allocate power between radar and communication such that we can maximize the detection probability subject to some rate threshold, so communication rate threshold. So this is some analysis on detection versus communication based on a passive ISAC transceiver, passive sensing receiver. This is a passive sensing receiver. And another interesting trade-off is the estimation versus communication, which has been studied in our recent work submitted to ETSP. So we can see the ISAC transceiver. This is a monostatic. So you transmit, the transceiver will transmit and receive by itself. Okay, so this is called a monostatic setting. And we transmit a common waveform or shared waveform X to both sense a target and to serve multiple communication users. And then we use this metric. This is MSE of the target response matrix, which is defined as the inverse of the covariance matrix of X and its trace. Okay, so the trace of the inverse of Rx. And we need to design this X to minimize the estimation error subject to some communication utility functions like SINR or communication rate. So this is again a trade-off function, a trade-off design. As you can see, they have contradictory design objectives. So they have MSE, the estimation errors, and they have, for example, SINR or communication rates for the communication users. Okay, so this is another design. So estimation versus communication. And in addition to this native performance metrics, so by native performance metrics, we refer to like the detection of probability, the false alarm probability, the mean squared error, and so on. So the researchers are also thinking about, can we define a novel metric for sensing from the perspective of information transmission, but this is actually not based on an information theoretical perspective. So some efforts are including, for example, to define a sensing capacity. So we all know that in the radar system, the radar process the echoes by using, for example, the resolution unit. So we can have angle Doppler delay resolution units. And in each unit, this can only accommodate one point target, okay? So we have a resolution in range, resolution in angle, resolution in Doppler, and we can have a maximum detection range and maximum detectable angular interval and the maximum detectable Doppler. So by using this, we know that these are actually the maximum distinguishable pointer targets in the radar system, which is defined by its physical limit. So the maximum detectable range, angle, and Doppler under their resolution, okay? So in this sense, we can define a capacity metric for this. But this capacity metric is actually very restricted to the identifiability of how many targets can be distinguished. And in another sense, this is another paper on defining the sensing estimation rate, which is actually based on, let's see, somehow mutual information for the estimation. So by estimate a target, you can somehow remove your uncertainty in the target. So this is somehow a process to acquire the information about target. So based on this view rate, we can define the so-called estimation rate by divide the mutual information by the time, okay, the time duration. So this is another definition. And in this paper, they have defined this estimation rate, and they have considered the trade-off between estimation rate and the data rate. So these are some failure trade-off. And some other important trade-offs, let's see, for example, the trade-off in the ISAC channels and the cross-layer trade-off. So in ISAC channels, the trade-off appeared because the sensing and communication view the channel propagation paths from different perspectives. For example, let's consider this scenario where we have a vehicle both as a communication user and a target. And then from the communication perspective, you can see there are multiple propagation paths from the transceiver to the user, okay? And so from the communication perspective, we should exploit all these paths, no matter it is line of sight or non-line of sight paths to transmit information. But from a sensing perspective, imagine that this non-line of sight path is also cluttered. Then you can see that the sensing, from the sensing perspective, it only cares about the line of sight path, so which is actually the target path. And the clutter can be harmful to the target. Okay, so there are some inherent trade-off in ISAC channels, and you will need to consider how to optimally balance the resource allocation on different propagation paths and the different channels. And there are also cross-layer trade-off because sensing can not only be done in the physical layer, but also in a higher layer. For example, like I said, when we do recognition task, we are considering the what the target is, and then the performance metric can be the recognition accuracy. And then there is a trade-off between this higher performance metric, higher layer sensing performance metric, and the physical layer communication performance metric. For example, if you have a Wi-Fi system to do both, one for sensing phase and another time duration for the communication phase, then how can you optimally allocate time resources on these two phases to balance the cross-layer performances on the target recognition and physical layer communication? Okay, so this is about the cross-layer trade-off. Okay, then let's come to the waveform design of ISAC. So actually, there are actually 4 types of waveform designs. Like I said in the previous slides, we can have time division, spectral division, spatial division, and a unified waveform. But from another viewpoint, we can split all the ISAC waveform designs into 3 types. One is sensing centric. This means that we design an ISAC waveform based on a pure sensing waveform, for example, a radar waveform. So this means that we embed the communication bits in the radar waveform, but in that case, we can only implement limited communication performance, but we can guarantee almost 100% sensing performance. So these are some classical sensing-centric designs. For example, this is a very first work on the dual functional radar communication, or ISAC in the literature, that they are using the pulse interval modulation to carry information bits on the radar pulses. And this is another design published on 2016, where we have a MIMO radar. We use main beam to do targeted detection and use side lobe to transmit information. And we can also use index modulation to, for example, this is a so-called MIMO frequency age radar, where we have different frequencies transmitted on different antennas. And we can use these frequency combinations to represent some communication code words. And in all these designs, like I said, sensing performance is perhaps 100% guaranteed, but the communication data rate can be very low, and this can all be applied to only limited communication applications. So another design is called communication centric. This means that we are using a communication waveform, a pure communication waveform like the OFDM waveform to sense the target, like in this very classical paper published on HV proceedings. They're using OFDM communication waveform to do radar sensing. And the review that using OFDM, you can have decoupled range and Doppler processing. But you will suffer from very high PAPR, which we all know, okay? And another design, this is based on a communication protocol 802.11ad, which is again a WLAN protocol. They're using the channel estimation field of this frame structure to do the radar. And this is composed by GLA sequences, which is favorable for sensing. But in this communication-centric designs, again, we have high data rates and 100% communication performance, but the sensing performance may not be guaranteed because our sensing performance is constrained in the default communication waveforms and protocols, okay? Then finally, we can also consider joint design, which can be a co-design of the communication and radar functionalities from the ground up, which is not based on any given radar or communication waveforms. So for example, we can have such optimization problems where we minimize the communication multi-user interference and a weighted combination of the radar waveform similarity subject to some utility functions, okay? So this rho can be a weighting factor from 0 to 1. And if you vary this rho from 0 to 1, you can see you can change smoothly from 100% radar performance to 100% communication performance, such that you can have a scalable trade-off. And the sensing and communication-centric design are actually two endpoints on these trade-off design curves. And in this joint designs, we can have high data rates, we can have radar reliability, but we may suffer from higher design complexity, because in previous design, we all based on existing radar or communication waveforms. But here we need to design a new waveform from the ground up. Okay, so these are three types of the waveform design. And then here is the receiver design for ISAC receiver. And this is a basic structure for the ISAC receiver and receive signal processing problem. Or we have, for example, a combination of target return or target echo plus the communication signals, and they come together and can be fed into the antennas, passing by the LNA and down converter and AD, and then come to the baseband signal processing. Then in the baseband processing, we have communication signal processing, we have sensing signal processing. And of course, they will interfere with each other. So there should be some coordination block within these baseband processors. And in communication signal processing, we need to do data demodulation. For sensing signal processing, we do target detection, estimation, recognition. Okay. So this is a toy model actually proposed by this paper. Although this is a toy model, but it can provide us some very profound insights. So we have a combination of communication signal and radar interference and the noise. So here the radar interference is modeled as a very narrow pulse with a very high amplitude PR here and with an unknown phase theta here. So because the radar always use constant modulus signals, okay? So the amplitude can be fixed and known, but theta can be unknown. So the problem is how to design the optimal decoder for the communication signal in the presence of the radar interference. So we can average over all possible theta, and this will yield this optimal decoder, which is here the I0 is the Bessel function, okay? So in different cases, for example, if the radar interference is small, then then this part can be omitted, and this becomes treat interference as noise decoder, which is well known in the information theory, so TIN decoder. And if the interference is large, then this Bessel function can be approximated as here. Okay, so this can be a successive interference cancellation decoder, which means that we need to first cancel the interference of the radar and then decode the communication symbols. So this is so-called ISAC decoder. And so the inverse problem can be how to design the constellation to maximize this rate, the communication rate in the presence of the radar interference. So this can be modeled as an optimization problem. So as you can see, there are two problems here. One is optimal decoding and one is optimal constellation design. So in optimal decoding, you can see that with this optimal decoder, these are the optimal decoding region in the presence of a radar interference. And in these designs, they solve this optimization problem in the presence of the radar interference. Then you can have this optimal constellation designs under different symbol error rate constraints. For example, 10-3, 10-5. Okay, so you will end up with different constellations. Then this provide us insight on how to design a practical ISAC receiver. Okay, so again, we look at this block diagram. We have communication signal, we have radar interference, we have noise, and it can be arranged into a matrix version as this. And the idea is to do iterative symbol decoding and interference recovery and cancellation. So this is obviously based on this SIC decoder design. And this can be, so for example, we have this B as the symbol to be decoded, and HC can be the communication channel, and this alpha is, and this alpha can be the radar interference to be recovered from some dictionary of H alpha, okay, HR, okay. So we can first decode this B, we can have a B height 0, and we subtract this decoded signal. And obviously we'll have an error here. So this error we call the V. And then we have this V, and we have this alpha, we have this equation, and we can formulate an on-grid compressed sensing problem to recover the decoding errors and radar interference. Because we believe that the error can be sparse, because most of the elements in this vector can be 0. And the radar signals can be sparse from some dictionaries, okay? Then we can formulate this on-grid compressive sensing problem to iteratively recover decoding errors and radar interference. And by recover these errors, we can have a symbol reading modulation like this. And these are some of the results. So when we increase SNR, we have the reduced SER and reduced waveform, radar waveform recover MSE. So this is from another paper published on actually JSTSP. So these are some basic designs and basic principles for receiver design in ISAC problems. And now let's look at the communication assisted sensing aspect, which is actually to have sensing supported by default communication frame structures and networking architecture. For example, here we use 5G NR frame and the CRAN architecture to support sensing. So we know that in the NR frame, we have many synchronization and reference signals like PBCH, PSS, SSS, PBCH, DMLS. So these are two slots for an NR frame, new radio frame, okay? So you can see, in addition to the data symbols, there are lots of fixed or reference signals here, and you can use reference signals to do sensing, or you can use both to do sensing. But there will be some problems here. One is that in the frame level designs, if you want to use a default communication frame to support sensing, then we know that the bandwidth may be limited, because we know that in NR frame structure, in the sub 6 gigahertz, one subcarrier can be up to 100 megahertz. And this is far from enough for accurate high precision sensing, which requires sensing resolution at a centimeter level, let's see. So there could be limited bandwidth for high precision sensing in the communication by using communication frame. And there might be self-interference, because for example, in this figure, we can have different mode of sensing. We can have monostatic sensing, which means that this transceiver is transmitting and then receiving by itself. So this is monostatic sensing. And we have downlink bistatic sensing or uplink bistatic sensing. So this means that the transmitter and the receiver, sensing transmitter and sensing receiver are separated. So this is called a bistatic. So you can, from the downlink perspective or uplink perspective. But if you are using monostatic sensing, then inevitably there will be self-interference. Because as you can see here, for example, here one OFDM symbol can be up to several microseconds, let's see. But this several microseconds can be translated into, let's see, hundreds of meters in a sensing perspective. Then this means that when you transmit some signal, even when you just transmit one OFDM symbol, then this echo signal for within to sense a target within hundreds of meters, then this echo signal will be reflected instantaneously. Okay, so this will cause self-interference because you are not finishing the transmission. Okay, so this is another very serious problem. Self-interference. And then an unknown data payload in bistatic sensing. This means that when you wish to use separated transmitter and receiver to do sensing, bistatic sensing, when you try to leverage the data, then this data can be unknown to the receiver. Okay, then the problem is then how to recover this data and facilitate the sensing process. So there are some challenges here, but there are also some solutions. For example, the limited bandwidth can be solved by, let's see, carrier aggregations. And the self-interference can be somehow resolved by full duplex technique. And unknown data payload, it can also be somehow resolved by, for example, some more advanced signal processing technique. Okay, so these are some frame level challenges. And from network level if we are using, let's see, a CRAN architecture where we have lots of remote RF front-end head, and which are connected by a BBU pool, so baseband unit pool. Then there are lots of challenges here. One significant challenge is that is intercell interference a friend or foe? Because in the pure communication network, we always treat interference as harmful, especially intercell interference. And we want to remove the interference. We just want to mitigate this interference to guarantee our communication performance. But in an ISAC network, this interference can come from the target. So it can be the reflection from some target that you are interested in. So intercell interference may not be, cannot be simply removed. You need somehow recover it and extract useful information, useful target information from the interference. So is intercell interference a friend or foe? And then the second question is, the target return can be an outlier in the CRAN scheduling because the target return is uncontrollable. So in a pure communication network, you can somehow control and schedule the transmitter and the receiver. So when you are going to transmitting and when you are going to receive the signal, okay? So you can do this fully controllable scheduling. But the target return can be an outlier because it is unpredictable and uncontrollable. So it is an outlier in a CRAN scheduling. And finally, there's a problem on network synchronization because in this network, if we want to do network sensing, we need all the sensing transceivers to be synchronized at a clock level. So like I said, if the synchronization error up to, let's see, nanoseconds, so let's see 10 nanoseconds, this can be translated to some ranging errors in, let's see, several meters. Okay, so this is again unacceptable for sensing. So this will impose very high requirements in the network synchronization at a clock level. So these are some challenges in the sensing supported by communication frame and CRAN architecture. Okay, then finally, I would like to talk about some topics on sensing assisted communication. So actually, communication is always assisted by sensing. I assume that most of us are from the communication background. Then we know that we have spectrum sensing, we have channel estimation, we have multi-user detection, and these are all based on the sensing technique. Okay, so you need to, for example, to sense whether the spectrum is occupied or not, and you need to estimate a channel before you transmit information, and you need to detect users in the multi-user communication scenarios. Then what is new in the ISAC-based framework about this sensing-assisted communication? Let's see, these old sensing techniques, sensing-assisted communications, are actually device-based sensing, which means that the sensing is based on a device attached to the sensed object. Okay, so this is a cooperative sensing. For example, if you are sensing the spectrum, you're actually receiving the signals actively transmitted from some users. Okay, so this is a device-based sensing. And for ISAC, we are actually more interested in device-free sensing, so like radar sensing. So we want to sense some object that without being attached to a device, an electronic device. So in other words, this is actually a slogan proposed by many recent 6G visions, like that we need to sense and connect the unconnected. So in the previous device-based sensing, we have all these systems that are connected into the networks. But if we want to sense some targets objects that they are not connected, then we need device-free sensing. So this is a more interesting scenario in the ISAC-based framework. So these are some previous works where we use a sensor to facilitate the millimeter wave communication beamforming. For example, in these works, we have a millimeter wave base station and with an extra radar system here. And they're using this radar beam to receive echo signal from a vehicle, let's see. And by using this echo signal, they want to accurately formulate a communication beam towards these vehicles. And if we are going to do the conventional beam training using communication-only training, then, for example, if you have, let's see, 32 transmit antennas and 32 receive antennas, then you will end up with 1,024 beam pairs if you are going to use exhaustive search. And if you have some prior information provided by, let's see, GPS sensors, then you can reduce this beam pair searching to, let's see, 475 beam pairs. And if you're using radar AD scheme, then this can be further reduced to 32 beam pairs, okay? So this is to use an extra sensor to facilitate millimeter wave communication beamforming. And you can also use vision-based sensors or LiDAR, okay? So these are all based on an extra sensors. So again, if we recall that we have integration gain and coordination gain in ISAC, we see that coordination gain is achieved by the mutual assistance from the sensors to the communication. And this is achieved by reducing, for example, the training overheads, which is, however, at the cost of an extra sensing system. So we will sacrificing the loss of integration gain, okay? So how about we use the ISAC-based system to do sensing-assisted beam tracking and prediction? So imagine that we have a roadside unit serving a vehicle, and it provides both sensing and communication services to this vehicle by using an ISAC signal. So by using conventional beam tracking scheme, which is based on pure communication protocols. For example, here we have the beam training schemes where we first send lots of pilots from the ICU to the vehicles here. And then when the vehicle receives these pilots, it will reflect Now it will feedback the best beam to the ISU, and then the ISU will transmit the data on this beam. So this is a beam training protocol. And at each data block, we need this beam training first, and feedback, and beam training and feedback. And if we do beam tracking, then this means that we have some prior information about the beam in the previous training or tracking process. For example, here we have the first step, beam training, and in the second block, we know that the optimal beam should be within some small interval of the previous optimal beam. So we're just using a limited number of pilots to do to search the beam, okay? And then we still need this feedback. But if we are going to use ISAC block, integrated sensing and communication block, then we do not need this feedback and this tracking and this training overheads. So this is because, so let's see, if we have a ISAC signal to do both communication and sensing, then there's no dedicated downlink pilots, okay? Because we're using this ISAC signal to do sensing. And there's no uplink feedback is needed because we are using the reflected echo from the vehicle instead of its feedback. And we can do continuous angle estimation based on the signal level estimation without the feedback quantization. Because in order to feedback an optimal beam, you should first quantize this beam into bits and then feed it back to the ISU. And finally, we can have a significant meshed filtering gain over conventional, let's see, beam tracking, because we're using the whole block to do sensing, but here we're just using a limited number of pilots to do sensing. But since we're using a monostatic sensing setup, we actually need full duplex because of the self-interference. So remember that if you are going to do monostatic sensing, then there's a need to cancel the self-interference, okay? So here are some results. So if we are going to use the ISAC-based scheme using, let's see, a common filtering technique, and when comparing with some well-known technique in the literature of communication only in beam tracking, then you see that we can have a steady communication performance in the communication rate. So this is a scenario where the vehicle driving towards the ISU and then drive away. So the communication rate first increase and then decrease. But if we're using communication only in beam tracking, then if the beam variation is very large, then it cannot keep up with the variation of the angle and the movement of the vehicles. Then the communication rate will suddenly go down to 0, okay? So these are some simple comparisons. And there are, of course, some very other important interesting topics like sensing-assisted physical layer security and sensing-assisted resource allocation. So for security, you can have active sensing to sense the channel of the eavesdropper. So in the conventional physical layer security designs, the eavesdropper's channel is very difficult to be known to the, let's say, the base station or transmitter. And with being equipped with this sensing functionality, it can somehow to estimate the eavesdropper's channel actively. Okay, so there is sensing assisted physical layer security, and for example, sensing assisted resource allocation. So we can have, for example, the sensing assisted cell handover, like in the vehicle case, we can by actively sense these vehicles when it's changing, during the handover of the ISUs, and the sensing assisted power allocation, bandwidth allocation, beamwidth allocation, all based on the sensed states of the movements of the users or the vehicles. And by using this sensing assisted resource allocation, you can definitely achieve higher efficiency than this communication-based resource allocation. Okay, finally, a summary. So we have talked about the performance trade-off. We have talked about signal processing, In addition, in particular, the waveform design, receive signal processing, and communication assisted sensing about using the NR frame structure, using the C-RAN architecture for network sensing and the sensing assisted communications. Okay, so remember we have two gains: integration gain and the coordination gain in ISAC. And here are some of our works on ISAC. We have several overviews. We have read-and communication spectral coexistence and ISAC waveform design, beamforming, hardware constrained secure design, and of course, vehicular ISAC transmission. So finally, I would like to remind you about our ISAC ETI, so you can visit this website, and you're very welcome to subscribe to our mailing list to receive the up-to-date news and activities on the ISAC related events. Okay, I think this is all for my talk. So any questions?